Hi, my name is Simon Crosby, and we're going to take a slightly different look at the edge in AI IoT. And my approach is really dev-centric. So it might be handy to start off looking around the audience and get an idea of how many of you are devs versus machine learning folks and so on. Dev, cool beans, machine learning types. Yeah, okay, typical. All right, cool. So I think all this AI stuff is arbitrarily hard. I mean, I do it, but it's arbitrarily hard for people to understand. And so we have to make it really, really easy for the average dev to go and do. So I would encourage you to go and play with Swim, which is an open source platform which makes it really trivial to go and build stateful distributed data-driven applications. I'm going to go through what that means, including things that just learn for themselves. Okay, so you don't have to be a data scientist or an expert in TensorFlow or whatever it happens to be. So go and play with Swim. It's out there, and it's a lot of fun. All right, so here's the little hamlet of Palo Alto. And in a given day, the traffic infrastructure in Palo Alto generates more data than all of Twitter. There is just tons of data out there, people. Tons, okay? And here's the slightly larger town of Las Vegas, which in a given day generates 60 terabytes from its traffic infrastructure, when the monster of Silicon Valley generates about 10 times that. Okay, so I want you to understand there is more data out there than we can ever reasonably shake a stick at. And if we're going to make sense of it, we have to do something other than load it up to the cloud in my data lake and dream that someone's going to process it later. All right. So I'm going to focus on a particular use case where most of the data is ephemeral. Okay, and it's true for a large portion of real-world devices. A lot of the predictive maintenance use cases and so on are easily attainable in this way. And when I talk about ephemeral data, I'm talking about data which kind of you don't really care about keeping. You care about the learning from it, but you don't really want to store the fact that the traffic light was green last Tuesday morning at 8:07. Okay. So here is a view, oh, it's cool, my video is working, of downtown Palo Alto, where each one of these, a digital twin of every intersection is predicting its own future. Okay? And so I want to take a slightly different view of how we could learn, given the vast amounts of data that are out there, and posit the idea that these digital twins of infrastructural elements can go and learn for themselves. Think about slightly differently. How might the world get smarter? It might get smarter a little bit like you do. That is, you look around and you learn from the data around you. Okay? And so this idea that all the data will be loaded up into the cloud and then somebody will build a model and it will be deployed to the edge, yeah, forget about that. Okay? Just forget about it. It's just not going to happen. There aren't enough people on the planet to do the job of building the models. We have to do it somewhat differently. Okay. So people tell me that, say, Palo Alto or Las Vegas is a cloud scale problem. And to be clear, my use case here, I'm going to go through one, but it's broadly applicable, is to predict what's going to happen in downtown Palo Alto or Las Vegas or Houston or New York. And sure, the cloud can solve these problems. The cloud can go wide. So at 30,000 events per second, sure, there are 30,000 servers up there doing AWS Lambda. No problem. It's awesome. But it's wide, okay? And I'm going to take a slightly different view of that, which is that if we process information statefully, locally, we can do things quite differently. So if I sit in my house, I live in Seattle, and I simply look at the sum of the times per event that I have to pay, it's, maybe I'm doing a bunch of programming and AWS Lambda is going to take some time to learn my code, and I'm going to use the database and everything else. I might be doing something like 700 milliseconds processing per event and only 1.1 milliseconds of CPU time. You know what that is? That's 99.999% wasted. And you know what? It's not that the cloud guys are evil, but you are going to pay. Okay? Let me phrase this whole thing differently. We have given the last 5 generations of Moore's Law up to REST and databases. Okay? Large amounts of infrastructure sitting, waiting around, doing nothing. Okay? So, Palo Alto, sure. I can solve these problems in AWS, or in Azure, or in Google. It's $6,000 a month, more than anybody will pay. Okay? But most importantly, it's 10,000 times slower than if I try to solve this problem at the edge in a stateful manner. Okay? So it's not the cloud guys are evil. They're awesome. It's just that the tools that they have, REST and databases, are not easily suited to the problems which we have at the edge, which is tons of data and really stateful processing. So if we go back in time, by the way, there's nothing new in computer science at all, go back in time, rewind the clock, and go back to stateful processing, we can do amazing things. By the way, if we just get out of the cloud, what can we free up? About a teraflop. Let me show you a teraflop. Oh, let me show you 2 teraflops. It's called the NVIDIA Jetson. Okay, just an ARM and a small GPU. All right, so you get the general shtick here. This notion of traditional processing, I have an application, I have some data, and I'm going to use my compute and database and get insights out. I want you to think of the applications somewhat differently. I want you to think of applications as things like balloons that aren't inflated, and then they get inflated by the balloon and become valuable because they're now solving problems at scale. They automatically scale because data makes them scale. The application model is built by the data. I'll be very clear, there aren't enough data scientists out there to build models of all the things we need to model. So how about we build applications which can build models for themselves? Okay, so I'm going to spend a little bit of time going through each one of these. All right, so a little advertisement for Swim, and then we'll get it off it. I want you to think of LinkedIn for things. And so I'm going to get back to this processing model, which is Swim. By the way, it's also present in React in many ways, okay? So, what you could think of here is Swim specific, but in general, the pattern holds. So for everything out there, in my case, every sensor in Palo Alto or in Las Vegas, it has a concurrent stateful digital twin, which I'm just going to call a web agent, and you'll understand why I call it a web agent in a minute. It's just a little tiny object, okay? It's sitting in memory someplace. And each one of these things is responsible for cleaning its own data. So it will concurrently process all updates from the real world thing and statefully represent it programmatically in a useful form. Hey ho, nothing new here in computer science, right? We get this. It's object-oriented programming. These are just concurrent things. I'm going to create one for everything I find in the data. Okay, so in the case of Palo Alto, maybe 10,000 or so these things are just going to get spawned off, and they'll each clean and statefully represent the state of that sensor. But there is this linked-in notion, and I'm going to allow things to link to each other based on information I find in the data. So, for example, proximity or containment, okay? And there are various other real-world relationships which we want to capture from the data. And later, you'll see other reasons for things to link, like correlation or mathematical transfers, mathematical computations we can apply to the data. Okay, now, similar to LinkedIn, if I link to you, I get to see your updates in real time. Well, whenever you post an update. So in Swim, processing it's a bit like PubSub. We're all familiar with PubSub. But in Swim, linking is it's sub for sure. I see your updates, but there's never any need to pub. I just process, change my state, and everybody sees it. Everybody who's linked to me automatically sees it. So LinkedIn, for things in a very real sense, you just put an update out there. You don't have to pub it. You just write the thing, and everybody sees it. Okay. And then we're going to, on a separate timescale, drop in operators for analysis. Things like find the average waiting time for a car, or learn and predict the future. Okay. And so we're going to build a graph, rather than having just a data pipeline, this notion of hauling all the data back to the cloud. I'm going to have a smart data flow pipeline, which is going to build relationships and do processing for me. Okay, so what am I going to have to do as a dev? I'm going to have to write a teeny little relational model which says, hey, this is the information from a traffic light, this is the information from an in-row loop. It links to a traffic light in the following way. So that's a little fragment of Java or Python or JavaScript, okay? And then data is going to show up and start to blow up my balloon. Okay, so for everything I find in data, I create a stateful, concurrent little object, a digital twin of that thing, which is going to take the raw data, process it, and then statefully represent it. By the way, I think the most profound thing AWS has done this week at reInvent is this schema repository, which lets you build this ontology for things in the real world. It's really cool. Okay, so and now we can create virtual things like intersections, and there isn't a real thing called an intersection. Well, it's not a sensor, which is a containment notion, right? And in the case of traffic, every one of the things, every one of the sensors is going to report Latin long, and then its data. So it's pretty clear how to build this thing. So the meaning of raw data is this object model, which you describe in your little program. And then we're going to create them on the fly. So building a model is pretty easy. Now, each one of these little web agents is going to take this ghastly information, which we typically find from deployed sensors, and statefully represent it. Note that the notion of I'm green is tiny, whereas I might be getting gigabytes per second of the data from the thing. The thing could be repetitive, right? And often in traffic infrastructure, for example, we'll get 10 updates a second from a thing, and they're all the same. It doesn't change. And so there's no reason to keep the original data. You just care about the state. Notice this. If you're a Spark person, one of the hardest things writing a Spark program is you can have squads of data from a noisy thing and no data at all from a quiet thing. And all of your state has to be stored in a database, like Cassandra or something sitting in there, which is trying to represent this model. Okay? What I've done at the edge here is go from data to state. Okay? And my things are stateful, and then I'm going to let them compute. So an app is one of these graphs which is going to go and compute for me. So it's pretty easy with, say 3,000 sections in Las Vegas, that's maybe 100,000 sensors. Great. Very easy to go off and build a graph composed of digital twins of the real world. But there is another piece of information which is really interesting. And that's because I'm getting a Latin long for every sensor, I know where it is. Okay, so the simple step of, hey, I want every one of these intersections to go and learn for itself. Learn for itself from the information that it has, plus information from its neighbors, which is pretty obvious if you want accurate information, is very simple. I just reach in and say, hey, link to your neighbors and go and learn and predict. And all of that stuff is just baked in. And so they go and do that. That is, they are actively and concurrently processing their own data. They're all linked to their neighbors, and then they'll go and learn. Okay, now, and then they'll go and learn bit, I guess there's a little bit of hand waving in there. Maybe I should have Mickey Mouse on my slides. I'm about to explain how we do that, but all the code is open source, so you can just go and grab it yourself. Notice that this is a world which continually computes. Okay, I'm not storing anything other than the state of each one of these digital twins in memory. So the learning notion, and we're a startup, so we're 20-odd major customers in. It's all working so far. The learning approach is this. Dynamically, at runtime, when you instruct a digital twin to go and learn, how it learns, it basically dynamically dimensions a DNN, a fully interconnected DNN, 3 layers deep, in which all the weights are random numbers. It forms an input tensor from the sensors that it can see. Notice we've done this beautiful thing, which is go from data to state, and all of the state is visible, and then just throw it through. Now, the first time, you're just going to get some prediction, which is no better than a guess, all right? But when we have this beautiful thing called the real world, and we can observe it do its thing, take the difference, and backpropagate. Okay? If you want to, you can grab me afterwards and say, how do we deal with time? I'll show you how we deal with time. But if you do this enough times, either you're going to get good or you're going to get bad. And the good thing is about this is you can track that error. If the error is diverging, yeah, you're in deep trouble. If the error is converging, pick yourself an operating point and then run. Okay? And all the applications we've dealt with thus far tend to be convergent. And so you pick your operating point and you're in good shape. By the way, we have streaming analogs to just about every algorithm you could find in Spark or Flink. Okay, so this isn't the only thing. Okay, so an application looks very different. In Las Vegas, there are 3,000 intersections, each of which is predicting its own future and streaming the result. So rather than having to go off and have a data scientist build me a model of Las Vegas and then train it and then push it to the edge and hope like hell that overfitting and underfitting don't grab me, every single one of these intersections is going to learn for itself and stream predictions. Okay? And these predictions, in our case, are presented through an API in Azure for this use case, for this customer. And those get pushed directly into Uber's Kafka or Waymo or Lyft or wherever, okay? So we're producing streamed predictions which are directly useful to customers. So it's not like the city of Las Vegas can do anything with this or the insights. They're nice people, but the people who can make use of the data are FedEx and Uber and Lyft and Waymo. Okay, but the key thing here is that the application itself, you just describe this simple object relationship. So in 600 lines of code, I've built this application which scales automatically to as many intersections as I have. And then each one of these things computes for me. We've used learning as an example, but it could be compute the average waiting time or something simple. I often get the question of, well, where does this stuff run anyway? And so I think it's important to redefine the notion of edge. Edge is not a place. It's a way of computing. Okay, so cloud for me is about rest and databases. If you have something which fits into that pattern, great, stick it in the cloud. But edge computing is not that. It's not rest, it's streaming. It's stateful, and it continually computes. Whether you decide to store the data or not, I don't care. But it's about computing on the fly. So I don't care about where this stuff runs. I care that I am the first to get my fingers on the data, okay? So we track 100 million endpoints for a large mobile carrier. All that stuff runs in AWS. Okay, it just so happens we get the data from somewhere out there, and we just process it. Okay, so the edge is not a place. The key thing that Swim will teach you, if you go off and use Swim, is that the edge is in a place, and that these little web agents can run anywhere. And now we get this notion of web agent versus, say, Istio and Kubernetes. Yeah, there isn't a service mesh. They just move around. And so Swim automatically moves computation to the right place. And so what you'll find is that these little web agents which are cleaning data and dealing with the really noisy stuff tend to run at the real physical edge. But if I happen to have an instance in the cloud with a GPU attached, the computation, which is intensive, relating to solving models and so on, will naturally migrate there. It just moves. So Swim smears computation a bit like peanut butter from the physical edge up to the cloud. And it automatically migrates tasks around. So you might say, well, I really care about this stuff, and I'm going to put a GPU locally in my data center. Fine. Swim will just move that on the fly to where the resource is available. Okay? And that's the cool thing about Swim, is that this notion of thinking about things, the embodiment of learning in a thing. Yeah, whatever, forget that. It's software, people. Software eats hardware. What we want to do is process data statefully, okay? So if you walk away with one thing out of this, it's that stateful processing is the answer to most of your problems. Last slide, and just a couple of observations. First of all, these models which are built by data, so I've just described a very simple object relationship. Models built by data are constructive. So not a line of software changes between Palo Alto, Las Vegas, Houston, New York. It just works. Just feed it data, it will build a model, the model will solve itself. That's awesome. That's a real one, okay? These digital twins, these web agents that learn, use very simple models, okay? So an intersection, say, is maybe 2,000 odd sensors or so in the tensor, which goes in the model. Small, fits on a very small GPU. Fits on TPU nicely, okay? In my world, over and under fitting, which are real problems related to training and the accuracy of your training data, are just non-issues. I care about this intersection only. And the model which is built by this intersection, given what it can see, is totally useless 300 yards down the road. Okay, I'm not trying to come up with a general model of traffic. I'm trying to come up with university and Middlefield in Palo Alto only. Cool, just let it run. Okay, so they tend to be very robust. We can learn on more data than you could ever put in your data lake. Okay, we learn on real-world data. Okay, in a use case that I mentioned briefly for 100 million endpoints for a large carrier, we're dealing with 1 terabyte an hour. It's lots. Okay, so if you learn on continuous data, it leaves us to chance. If the real world changes on you, cool, you just change too. So we can train on full resolution data far more than you could ever store. Okay, it's a different world, it's a different approach. You can run the software in AWS, or you can run it on an edge device, or smear it across both. We just don't care. It's a different way of computing. The edge is stateful, and stateful computing is the way to make sense of vast amounts of data. I'll leave it at that. All right, cool. Thank you very much.